Suppose you have a function f of x, and let's say it's given by a really complicated and difficult to compute expression. Now let's say you want to have a computer repeatedly evaluate f, perhaps even millions of times. For really complicated functions, this can take a lot of time and can get quite costly. This is where approximating f by a polynomial can provide a solution. Because polynomials are comprised of just a few basic algebraic operations, evaluating one often takes less time than evaluating a more complicated expression. One example of a polynomial approximation is the Taylor series for sine of x. As we plot more and more terms of the Taylor series, we get closer and closer to sine x, or in other words, these polynomials converge to sine x. Another way of saying this is that we have a convergent sequence of polynomials whose limit is sine of x. Now, using this concept of convergent sequences of functions, we can make the somewhat fuzzy notion of approximation more precise. For our purposes, approximating a function f by polynomials simply means finding a sequence of polynomials that converges to f. And this definition is really quite natural once you realize that approximation is all about minimizing error. To minimize the error, I can just go further along in the sequence to find a polynomial that's close enough to f that its error is as small as I want. And this leads me to the theorem that I'm going to informally prove in this video, the Weierstrass approximation theorem. It states that as long as a function f is continuous on the interval ab, then there is a sequence of polynomials Pn that converges to f as n goes to infinity. In other words, every continuous function f can be approximated by polynomials. Now, technically, we can find a uniformly convergent sequence, which is a bit stronger notion, and roughly means that the rate of convergence doesn't depend on x. But that's a bit beyond the scope of this video. Let's take a quick detour to talk about some of the key ideas behind why the Weierstrass approximation theorem works. A Gaussian blur is a type of blurring operation you can apply to an image to make it smoother. For example, here's what it looks like to blur a chessboard. And if we reverse the blurring, we see that our image gets closer and closer to the original chessboard. So in some sense, blurring an image slightly is like approximating it by a smoother image. And despite being so simple, this idea is actually the key behind Weierstrass's approximation theorem, except instead of approximating images by smooth images, we're approximating continuous functions by polynomial functions. In order to go further, we need to understand how a Gaussian blur works. Informally, a Gaussian blur averages nearby pixel values together. For example, at places where white and black tiles meet, the Gaussian blur combines white and black to make gray. More formally, this type of local averaging is expressed through the convolution operation, which takes in two functions and produces a third function that's in some sense a combination of the two. A Gaussian blur is just the convolution of one function, or in the discrete case an image, with a Gaussian function, which represents the normal distribution or bell curve. The convolution of two functions f and g is defined by the following integral. And even if you're familiar with calculus, this definition's connection to averaging or blurring seems unintuitive at first, but I hope to illustrate this through examples. Let's first try to understand what convolution is doing in the context of a Gaussian blur. Just to simplify things down to one dimension, let's take one row of the chessboard and assign the value 1 to white squares and 0 to black squares. In doing so, we get a square wave, which will be our function f. To obtain a Gaussian blur of this square wave, or more technically a Gaussian transform since we're dealing with functions, we'll use a Gaussian function for g, which depends on a parameter h that controls the width or the variance of the Gaussian. And as we'll see, a larger h means a larger blur. So for a particular value of h, the Gaussian looks like this, and its convolution with f is like a smoother version of f, which is exactly like in the case of a two-dimensional image. And as we increase h, f convolved with g gets even smoother. As we go backwards and decrease h, the Gaussian gets narrower, and f convolved with g becomes closer and closer to f. So really, this just confirms the same intuition we built in the Gaussian blur example, but just with more mathematical specificity. Let's look at another example, which will hopefully make the definition of convolution seem a bit more intuitive. Let's say you have a set of data points, and for simplicity, Let's represent this data as a continuous function f of t. Maybe this data represents new COVID cases, or a stock price, or someone's heart rate over time. Now let's say we want to calculate the average value of this function over a certain interval. For example, the average new COVID cases over a 7-day period. As we'll see, this type of moving average can be represented by convolution. Now the average value of a function f on some interval, say from a to b, is simply the integral of f of t from a to b divided by the length of the interval, b minus a. For those unfamiliar with integration, an integral is just the area under the curve, in this case from a to b. An integral is sort of like a continuous sum, in the sense that you're adding up the areas of rectangles under the curve. So just like with finite averages, you're adding up a certain number of values and then dividing by something, in this case the length of the interval, but with finitely many points, you'd divide by the number of points. Let's try to show exactly how averaging can be expressed in terms of convolution. This will require some calculus, but I'll try to explain the gist of things and the main conclusions. Let's first change our interval slightly to be centered at x and have a length of h. Then our average becomes an integral from x minus h over 2 to x plus h over 2. Now let's look at a step function over a similar interval, but centered at 0 instead of x, and with a height of 1 over h. The function g of t minus x is the same step function, but centered at x, so that it lines up with the interval we're averaging over. Notice that taking an average over this interval centered at x is actually the same thing as integrating f times g of t minus x, since everything outside the step function is 0, and the 1 over h can be brought inside the integral. Next, we can actually replace t minus x with x minus t, since g of t is symmetric, i.e. it doesn't matter whether x minus t is positive or negative. The final step is to rewrite this integral as one that goes from negative infinity to positive infinity, in order to fit with the definition of convolution. Because g of x minus t is 0 outside of the interval x minus h over 2 to x plus h over 2, this doesn't actually change the resulting integral, so this shows that we can represent a moving average by a convolution with a step function. Hopefully, this shows more concretely the connection between convolution and local averaging. Now the really cool thing is that when we let h go to 0, f convolved with g actually gets closer and closer to f, or in other words, converges to f. The reason for this, and I won't walk through all the details, but I encourage people who have taken calculus to do so, is that in the limit as h goes to 0, our original integral is actually equal to the derivative of the antiderivative of f. And from the fundamental theorem of calculus, which says that differentiation and integration are inverse operations, this shows that the limit as h goes to 0 of f convolved with g is equal to f. So now we've seen two examples of functions g, where when we let the parameter h go to 0, f convolved with g approximates f. And there's a special name for these types of functions, or rather families of functions, and they're called approximate identities. These are functions gh, meaning they depend on a parameter h, such that f convolved with gh converges to f as h goes to 0. To fit with our previous discussion on convergent sequences, we can reformulate this in terms of sequences of functions, and instead think of an approximate identity as a sequence of functions gn, such that f convolved with gn converges to f as n goes to infinity. So let's recap a bit. We know that if we convolve f with a Gaussian g, we get a smooth function. So because a Gaussian is also smooth, convolution in some sense transfers properties of one function to another. In this case, the smoothness of a Gaussian is transferred to the convolution of f with g. Obviously, there are many nuances to this, but intuitively it can guide us when it comes to polynomial approximation. In particular, we might ask two questions. First, is f convolved with a polynomial also a polynomial? And second, does there exist a sequence of polynomials Qn that form an approximate identity? Because if these conditions are true, then we've found the sequence of polynomials we're looking for to approximate f, and we can calculate them using the formula Pn equals f convolved with Qn. The answer to the first question is yes, and it really just requires a messy calculation, which I'm going to leave out and encourage you to verify instead. For the second question, I'm going to claim that the following sequence Qn is indeed an approximate identity provided you choose the constant Cn correctly. But in order to show this, we first need to determine some properties of approximate identities, which I'll do next. Very loosely speaking, approximate identities can be described by the following 4 properties. First, Gn is symmetric. Second, Gn decreases to 0 as you go further away from the origin. Third, the total area under Gn is equal to 1. And fourth, Gn becomes a quote-unquote spike at the origin as n goes to infinity. Another way of stating this last one is that the area under Gn gets concentrated at the origin. These properties held for a Gaussian and also the step function we looked at, and now let's try to verify them for Qn. Clearly, Qn is symmetric and decreases to 0 the further you are from the origin. The constants Cn are intentionally chosen here to make the area under Gn equal to 1, so that's satisfied automatically, and as n increases, Qn gets more and more concentrated at the origin. So very informally, we've shown that Qn is an approximate identity. We're now ready to informally prove the Weierstrass approximation theorem. So let's recap what's been done so far. Recall that for a continuous function f, we're trying to find a sequence of polynomials Pn such that Pn converges to f. We've shown that the sequence Qn forms an approximate identity, i.e. that f convolved with Qn converges to f as n goes to infinity. And if you take my word for it that f convolved with a polynomial is also a polynomial, or if you verified it yourself, then f convolved with Qn is a polynomial, and since it converges to f, we've now found a sequence of polynomials that approximates f, which is exactly what we intended. It's certainly not the best algorithm out there, but it's a really neat application of some deep ideas that show up a lot in different areas of math. Overall, I hope you learned something, and hopefully this video inspires at least a couple people to learn more about all the cool applications of approximate identities and convolutions and Gaussian blurs and all of the fun stuff that was talked about in this video.